Hi. In this last presentation of the regular sequential circuits playlist, we will look at binary counters. So after watching this presentation, I hope that you will be able to write VHDL descriptions for this type of circuits, and namely for universal binary counters and for modulus M counters, which we will look into during this presentation. The universal binary counter considered here is a bidirectional counter that can be preloaded with any given value, and that can also be cleared synchronously. You may pause the video at this point if you want to have a detailed look at the sequence of VHDL statements by yourself. But before you do so, let me call your attention to two important aspects. The first one is the difference between the asynchronous reset and the synchronous clear signals. The asynchronous reset is just the usual construct that we have already used it several times before. So if reset is high, then the register outputs are immediately set to 0. But when I say immediately, what I mean is that because the reset input belongs to the sensitivity list of this process, we do not need to have a rising edge in the system clock to set the register outputs to 0. That is to say, as soon as reset goes high, the process is activated and the register outputs are set to 0, even, I repeat, even if there is no rising edge in the system clock, and that is why the reset input is asynchronous. Now, on the other hand, if you look at the combinational logic segment, you will notice that likewise, as soon as the synchronous clear input goes high, then the next state values will be set to 0. However, the next state values will only be transported to the register output at the next rising edge of the system clock. So if there is no rising edge, the synchronous clear effect will, synchronous clear input will have no effect, and that is why this input is synchronous to the system clock. The second aspect deserving your attention is the need to perform a type conversion. And this is due to the fact that arithmetic operations are not supported on the standard logic vector data type. And since the signals underscore next and underscore register were defined as unsigned because we need to increment or decrement their value, we will need to go from standard logic vector data type into unsigned before doing these operations. And likewise, we will also need to convert back from unsigned into standard logic vector before updating the counter outputs. Finally, let me call your attention to the fact that we are generating two combinational outputs to indicate when the counter reaches its maximum and minimum values. Now, the modulus M counter presented in this slide doesn't support any other control input besides the reset signal, which is declared and used in the usual form. The thing to notice here is the way to force the counter reinitialization when the limit value M is reached. But the corresponding statement here is very much self-explanatory. As you may see by checking the full VHDL description of this block, which is presented in pages 82 and 83 of the book, this limit M was defined as a generic declaration in the entity description. So like in previous cases, I very much recommend you to open the corresponding VHDL files that are available in our course website and to use them in the Xilinx design environment to simulate the operation of these blocks and eventually to see what happens when you make any changes in in their functional description. Thank you very much for your attention.